Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we are discussing the epicyclic gear arrangement in combing machine only. So, in previous section we have discussed in general epicyclic gear arrangement, where we have discussed that there are basically minimum 3 components are required. One would be the sun, and other will be the planet, and third one will be the arm. So, that we have discussed in detail. Now, here in comber basically we need epicyclic gear to superimpose two different motions here. One is the intermittent rotation, which comes from the oscillating nipper shaft I. Another is the superimposed, it will be superimposed on a constant motion, which is basically cylinder comb shaft, and ultimately it gives motion to the epicyclic gear. Now, here if we see the intermittent motion, the magnitude of intermittent motion I is more than the constant motion C. Okay. Now, we will discuss in 3 stages, as we have discussed earlier in comber. In the detaching roller has 3 types of motion. One is the backward motion, second one is the fast forward motion, and third one is the normal slow forward motion. So, case 1 will be the backward motion. So, this is the case 1, where if the direction of the intermittent rotation is opposite in sense of the constant rotation. So, if I is negative and C is positive, then the intermittent motion will dominate, the intermittent I will dominate and cancel out the effect of the constant rotation, and the net effective motion will be the backward motion, that is a negative sense motion. Okay. Backward motion of the detaching roller, that is the rotational speed of the detaching roller, it is a O1 and it is negative, that is a backward motion. O1 is the motion where the intermittent motion is in opposite sense to that of constant motion, that is case 1. Okay. And ultimately the detaching roller will have the rotation of O1. Similarly, in case 2, the superimposed motion from the epicyclic gear train transmits to the detaching roller through the that is a gear train, where these motions are in the same sense. That means, the intermittent motion I and constant motion C are acting in the same direction, okay, which results the detaching roller moves in the forward direction in fast movement, that is the rapid movement will be there, and the rotational speed of the detaching roller here it is O2. In case 2 it will be rotational speed will be RPM will be O2 is a positive and assumes a greater value, that is fast forward speed. Okay. And the third one, case 3, the intermittent motion stops, it ceased to exist, it will stop. Only the rotational speed of the detaching roller comes from the constant motion, okay, that is O3 and it is positive. So, intermittent motion will stop and we will get the rotational motion O3 and it is a normal advance, that means slow advance will be there. So, 3 stages will be there, case 1, case 2, case 3. they will take place sequentially. Okay? They will not take place in simultaneously, they will take place sequentially. And the net movement of fiber fringe by the detaching roller will be as a function of all this speed of the detaching roller and their duration. So, what will be the net motion? So, T 1, T 2, T 3. So, T 1 at T 1 speed T 1 time it moves at O1 speed, T 2 time it moves at O2 speed, T 3 moves at O3 speed. This 3 will be actually then added and we will get the effective motion of the detaching roller if we know the diameter of the detaching roller. So, effective speed will be effective movement of the detaching roller will be pi d multiplied by 1 T 1, O 2 T 2 and O T 3 3. The time duration T 1, T 2, T 3 and detaching roller diameter is d of the detaching roller d d. Net movement of the fringe S and rotational speed of the detaching rollers T 1, O 2, O 3 and case 1 O 1 is the detaching roller speed negative. So, it is actually helping in overlapping the fringe, that is backward motion. Intermediate motion is in the opposite direction to that of the unidirectional motion. This is case 2, O 2 is the positive immediate after overlapping, that means fast forward will be the, because it needs fast forward, because here we have to actually have some detaching speed, that fringe has to come out from the lap forward portion of the lap. So, for that we need fast forward motion. Normal forward motion will have a problem. Okay? There, that can be discussed later. That the problem would be that it may that combing action may not take place, that is with by top comb the action may not take place, and if it is slow, then there is a chance of the small dust particles and short fiber can come through the top comb. So, that is a fast forward. Intermediate motion is in the same direction to that of the unidirectional motion, intermittent motion. And case 3 is that O 3 that is positively the intermediate motion is stopped. So, that is that it is not moving, that I is 0 and where there will be slow forward motion. So, these 3 motions will be there, as we have already discussed. This is actually the negative, that R is the backward motion, and here portion initial portion will be the fast forward and then the slow forward motion. So, that way we will get the V, whatever this distance it consists of the fast forward initially and the slow forward, and effectively with that example effectively it is a every nip there will be effective takeoff will be 31.5 millimeter. So, this is the epicyclic gear system of a comber, and the photograph is given here. Now, we can see here, now this is the schematic diagram of the epicyclic gear here. Now, A here, this A is a sun gear, A is sun gear. Sun gear has got the motion which is intermittent motion. So, A has got intermittent motion, just we must know. So, this is intermittent motion A, and this F, this is here, this F is the with 80/70th, which is arm, which rotates anti-clockwise, constant speed 36 rpm. For this example, it is a 36 rpm. It is moving at constant anti-clockwise direction. Now, the motion of the arm F, which will have a revolutionary motion of gear B and C, which are fitted on the shaft. Okay. So, this as the F rotates, the axis of B and C will have a revolution around the sun A, okay, and sun A drives B with the gear, and B and sun A, the B gets drive from A, rotational drive, and B and C are in the same shaft. So, they will rotate in the same rpm, B and C, and C ultimately drives T, which is output, and this output, from this output gear the detaching roller gets its motion. Okay. Now, A has got the motion which is intermittent. Okay. Now, F is the arm with 80/70th. Now, we can see here from this picture, the photograph, you can see in this photograph, this one is arm. Okay. This one is the arm, and on the arm we have the 3 wheels fitted. These are the basically the planets. So, here in actual photograph you can see here, these are the planets, okay, shown by the color, green color arrow. You can see green color arrows are there, okay, and here the sun is shown by the yellow arrow. You can see yellow arrow, this is sun A, here is the sun A, and in this this is the sun A. Okay. And planet B is by green color, dark green, and light green color arrow is shown showing the planet C, which is in the other side of the arm. Okay. That means, B and C are fitted in the same shaft, but loosely fitted on the arm, which only makes the revolution. This is the system here. Now, with example, now with a specific example we are discussing for the combing machine. Now, this is the diagram we have seen in the last slide. Now, gear F, which is arm, rotates in counterclockwise direction with a constant rpm. Here in this picture it is a 36 rpm is given. As one stands near the headstock, it looks towards the delivery side of the comber, that is the direction we can see. This gear gets its drive from the cylinder comb shaft through the simple gear arrangement. So, this is getting drive from the cylinder comb, that is cylinder comb shaft rotates in the same direction. So, that is why it is rotating in the same direction. On one side of this gear F, the 3 identical gears. So, that is 3 identical as we have seen earlier. So, 3 identical gears are required, like 3 identical, it is not here in this picture it is shown only one B, but actual in a photograph we have seen, just I will show you back. Here you can see there are 3 identical gears are there. You can see this is 1, 2, 3 identical gears are there. They are placed in 120° apart. Okay. That is 120° interval away from on the axis of gear A. So, that is why do you need 3 gears? Because it is only one gear will actually do the all this motion transmission, but 3 gears are required just for dynamic balancing, otherwise there will be vibration. So, similarly, on the other hand of the gear, that is a F, that is arm, other hand we will have similarly 3 C's, okay. C identical gears, 3 identical gear C mounted on the angular separation of 120° away from the axis of the gear F. So, again on the other direction we have 3 gears. So, this is basically 3 gears we need, because to have actually that dynamic balance. So, gear B and C are compounded having the same rotation, they are compounded. Here we are compounded, and the purpose of having 3 gears is to actually have dynamic balance in the epicyclic gear system, otherwise there will be vibration, sound will be there. Otherwise mass imbalance created at that place in the epicyclic gear would transmit vibration to the detaching roller, and hence mass variation in the delivery wave. So, we do not need any vibration, otherwise at the detaching roller system, if there is a vibration, it is a very weakest point. We are dealing with the fiber fringes, very parallel, very open fiber fringes. So, in that case, just to avoid any vibration, we need 3 identical rollers. From the point of view of rotational speed of this gear, there are 3 gears at each position B and C have the same effect. So, we do not need the 3 gears for the purpose of the rotational speed. Okay. Now, gear A is loosely mounted. So, gear A is loosely mounted on and coaxial with the gear F. So, that is why gear F is rotating unidirectionally, but gear A can rotate both positive and negative direction. That is why it must have the loosely mounted, it must be loosely mounted, but it should be coaxial with the gear F. A complex mechanism comprising of crank mounted on the gear cylinder gear concept, cam, swivel plate and swinging arm, actually this derives the motion of gear A. So, cylinders concept actually gets the simple motion, rotational motion, but the complex motion, that is a positive and negative direction motion, we get from all this combination, okay, complex motion mechanism, and this gives the drive to the rocking shaft also, that is a nipper shaft also. So, gear C drives the gear D. Okay. So, this gear C drives the gear D, that is also loosely mounted on the same shaft of gear F. So, gear A and gear D are loosely mounted on the shaft of gear F, which is arm. Okay. So, gear A, F and D are mounted on the same axis, and as they are loosely mounted, they can rotate at different speeds. So, that is important. So, they will have different rotational speed, but they are in the same direction. So, what we can see here, this actually this A gets drive from the rocking shaft, that is anti-clockwise clockwise direction, and F arm its constant motion from cylinder shaft, and the combination of this A and F, it gives drive to the detaching roller, and the D, and from D the detaching roller gets motion. There will be a gear ratio can vary from 3 to 4 approximately, that we will do calculation and we will see. Now, gear B and C revolves around the axis of gear F. So, they revolve in addition to their rotational motion which they are getting from gear A. So, gear A gives the rotational motion to gear B or gear C, but gear F, as it is fitted on the gear F arm gives the revolutionary motion, additionally revolutionary motion. That is why in this system, if we want to identify which one is arm, first we have to see which one is the planet, which are the planets. Planets means B and C will definitely be planets, because their actually axis moves, that is a condition, and A, it moves around A, that is A will be the sun, and the F, which the gear F is actually responsible for the movement revolution of the axis of B or C. That is why F is the arm. Okay. The gear F is arm here. The superimposed speed from gear F and A are transmitted to gear D of the epicyclic gear train, which in turn transfer the motion to the, that is the front and back detaching rollers through gear train. Okay. So, this gear train is not shown, but there will be a gear train, simple gear train will be there. Now, try to see the velocity ratios. First, we have to see the components. What are the components? Component A, which is sun, then it gives motion to B, then from B C gets motion, the same speed will be the B and C are in the coaxial same axis, and they are in the same shaft, they will have same speed, and C gives motion to D, okay, and there will be another motion which is F. Now, these are the different components. Okay. As I told, only number of columns will change, okay, depending on the type of number of moving elements. Earlier example, it was only A, B and C. Here we have 5 elements. So, that is why it is a 5 columns we have put. Now, first operation, it is a gear train as a whole rotates with the speed of y. So, they are locked, everything is locked, and arm is rotating at y speed. So, everything is locked, nothing, there is no movement. So, if arm rotates, everything will rotate at the speed of plus y. So, we will put plus y everywhere. So, for A is rotating at plus y rpm, B is also rotating at plus y rpm, similarly C, D is also rotating as plus 1 rpm, because F we are giving the speed on F. So, F is the arm. Now, what we are giving, we are actually locking the arm, we are making everything free, only locking the arm. So, if arm is locked, okay, the sun gear is rotating at speed of x. So, sun gear has got x speed, arm is locked. So, arm has got speed 0 rpm, and then we are giving sun gear which is A as I told that we have to identify the arm, planet and the sun. If we can identify, then the things will be very simple. So, x we are giving to the sun gear, and b, how the b will rotate, we know the number of teeth in A is 33 and number of teeth in B is 21. So, we can calculate the speed of the B. So, B will be on the negative direction, opposite direction, x multiplied by 33 by 21. Now, this x multiplied by 33 by 21 minus. So, this negative motion will be reflected in the same direction in the C. C will have the same direction and same magnitude. So, that is why it is minus x 33 by 21. Now, from C, D is getting motion. C has got the teeth, number of teeth is 29 and D has got 25 number of teeth. So, we can see it will be in the other direction, positive direction, that is x plus x multiplied 33 by 21 multiplied by 29 by 25. So, that is how we are getting the effective speed of the gear D, that is output gear D, when the arm is locked and A is given +1 speed. Now, if we add, so resultant speed of A will be x plus y and the speed of B will be y minus 33 by 21 x multiplied by x, and same will be on the C, and D will be y plus earlier speed, and then F will have y. So, if we add this thing, we will get this resultant speed. Now, from here the RPM of gear A, which is sun gear, which is we are getting x plus y, RPM of gear B and C, which are planet, will be y minus 1.57 x. This actually this is 1.57. So, that is x, and D will have 1.82. This will give you 1.82 x plus y, okay, and RPM of gear F, that is arm, is y. So, if we can calculate this, then from their actual speed, if we use actual RPM, then we can calculate the speed of each and every component. Now, let us see. So, RPM of gear A can be calculated, okay, that we can gear A F, F is a unidirectional speed, and from the speed of the machine and gear ratio. So, for various production rate nips per minute of the comber, so that we can calculate if the nips per minute of the comber is changed, then a gear F speed will change. So, let us take one example for a machine which is running at 240 nips per minute, 240 RPM speed, it is running nips per minute, and its speed becomes plus 36 RPM in anti-clockwise direction. So, this machine with this example is for the machine which is running at 240 nips per minute. Okay. In 1 minute 240 such complete cycles will take place. Okay. Now, speed and direction of rotation of gear F is always constant throughout the combing cycle, that is we have discussed. This arm is always constant, which is positive, that is counterclockwise anti-clockwise direction. Now, this is counterclockwise direction F, we have already calculated. So, the gear train ratio between the output gear D and the bottom detaching roller. So, as I told, we assume it is at 3.1 gear train ratio. So, that is a minus 3.1. So, counterclockwise rotation, that is positive plus rotation of the detaching roller corresponds to forward motion of the detaching and vice versa. So, my positive rotation will means the forward rotation, okay, forward movement of the detaching roller, and negative rotation means it is a backward motion. Okay. So, that way it goes. The diameter of the detaching roller is assumed to be 25 millimeter in this calculation. Now, here we can see the diagram of movement that we have already discussed. Here we will only concentrate on the detaching roller portion. Now, here if we see it is a say it is a 40 index number. Here typically around 6 to 7 it starts returning, that is backward motion, and it ends around 16 to 18. Okay. Then it goes from there to advance fast forward is up to say 26 around, and then 26, 27, then normal movement. So, that we will see. Here it is a normal movement, here also it is a normal forward movement. So, this one is the backward movement, this one here is the fast forward motion. So, with this assumption, with this we will see. Now, from the index number 6 to 16, 6 to 16, so 10 index number, it is basically 1/4 of the combing cycle. 1/4 of the combing cycle means the time duration is 1/16th of a second. 1/16th of second, how is it coming? 240 nips per minute. So, in 1 minute, 240 nips, that is for 1 nip, 1 cycle, it will be 60 by 240, 1/4, 1/4 second, 60 second. So, 1/4 second, for 1/4 second one cycle is taking place, one nipping is there, 1/4 second, and 1/4 of the combing cycle will take 1/16th of the second. That is how 1/16th comes. So, 1/16th of second, we should remember T1 is 1/16th of second, backward motion. Now, backward movement of the detaching rollers at that time, RPM of F gear is 30, that is counterclockwise constant speed. Now, RPM of gear A is 116 counterclockwise, that is in that direction, correspond to the movement about 4/10 of the gear A. So, 4/10, how is it coming? 116 is the RPM and 33 was the teeth. So, that means within that 1/16 second, 1/16 second only 4 teeth will move. So, that way we can calculate. So, 116 multiplied by 33 total gear divided by 60 in a second, and 1/16th by 16 it will be, that means number of teeth. So, we can see in case 1 backward motion of the detaching roller, putting the boundary condition this 6 to 16. So, 1/4 of the combing cycle, that means 1/16th of the second duration, RPM of gear A x plus y, as we have discussed that from the ratio, that 240 RPM nips per minute, gear A will rotate at 116 RPM in positive direction. So, x plus y is the sun gear A, x plus y 116, y is 36 from the table we have got. So, x is 80, x we have got 80, and from there RPM of gear D we have already seen in the table, RPM of gear D is 1.82 x plus y. So, if we replace y 36 and x 80, we get RPM of gear D, output gear 182. So, output gear RPM is important, and from there we can calculate the RPM of the detaching roller. So, what is that? So, gear ratio we have seen minus 3.1. So, multiplied by 120, that means minus 563 backward movement. So, at that RPM, detaching roller will move at the backward direction. Okay. And backward movement will be, that is the speed here RPM, and 1/16th of the second it is moving. So, diameter of the detaching roller is given, RPM is given, and 1/16th of second, within that time it moves backward by 46.06 millimeter. So, this is the case 1, okay, 1/16th of second. Now, you can see x plus y A, and RPM of gear B and C becomes y minus 1.57 x, RPM of gear D that we have already seen, and RPM of gear F will be y. Now, forward movement, fast forward from typically 16 to say 26 again. So, for case 2, fast forward motion from index roller 16 to 26 index number, that means again for to make it simplified. So, 1/4 of the combing cycle, that is again 1/16th of second it will move fast forward. Earlier for backward, and it is moving fast forward for 1/16th of second, that means 1/4 of the combing cycle. So, fast forward movement of the detaching rollers there, RPM of the gear is again same plus 36 counterclockwise, and from the gearing system at 260, so 240 RPM nips per minute. So, gear A rotates in clockwise direction minus 146 RPM, that we get from the gearing system, from the rocking shaft, and corresponding to the movement about the 5 teeth of the movement. So, minus 146 RPM. Now, we will use this minus 146 RPM. So, this is 1/16th we are getting, and case 2, that means 1/16th of the second, putting the boundary condition from 16 to 26. Now, RPM of gear A, that is x plus y, will be minus 146. This is coming from the gearing diagram, and RPM of gear F, that is y, is 36. From there we can calculate x, x is becoming minus 182, and RPM of gear D using the same formula 1.82 x plus y, it is becoming minus 295, and then if we get the gear ratio minus 3.1. So, detaching roller speed RPM will be plus 915, that is fast forward speed, okay, and fast forward speed, and the forward movement S1 will be, that is, this is the speed here, pi d diameter and 1/16th of second. So, it is moving at that speed 915 speed, and total, and for 1/16th of second total movement in the positive direction, that means forward movement will be 74, that is the fast forward motion plus. Now, third, normal forward motion of the detaching, where the F, that is y, will be 0 if there is no motion. So, it is becoming, so it is 26 to 40. So, it completes the cycle, and again it is go from 0 to 6, the total half of the cycle, that means 1/18th of second. So, this normal forward motion will continue for 1/8th of second. Okay. So, very slow forward motion of detaching roller, that is a normal advance. RPM of F is 36, counterclockwise again same. No, sorry, I have made a mistake here. This is will be there, but here this A will cease its movement. A will not have any motion. Okay, that means x plus y will be 0. So, here A will not have, earlier also I have mentioned here. So, A will not have any motion in this case. So, gear A will be stationary. So, RPM 0 will be there. Now, you can see here for 1/8th of second, that A will not have any motion, only the gearing diagram, that is the epicyclic gear, will get motion from the our, that is F arm will rotate at 36 RPM. So, RPM of gear A, which is x plus y, is 0, arm F is giving plus 36 motion. So, x will become minus 36. So, let us see what is the speed RPM of gear A, gear D, then 1.82 x plus y, that is minus 29.5. So, this is the negative direction, and ultimately what we will get if we multiply by gear ratio minus 3.1, that means we are getting the RPM 91.5, that is forward movement, the slow forward movement. So, forward movement of the wave, that is S3, if we try to calculate here, pi 25 is diameter, 91.5 is the speed in RPM, here 91.5, and here 1/8th of the second. So, this is 1/8th of second. So, we are getting effective movement, the forward movement is there 14.97 millimeter in half of the cycle, that is 1/8th of, sorry, that is half of the cycle, that is 1/8th of second, this much movement is there. So, net forward movement of the wave per combing cycle is S1 plus S2 plus S3. So, this is becoming minus 46.06 plus 74.88 plus 14.97. So, it becomes 43.79. Now, this we have tried to understand the basic calculation, how to calculate the movement, net movement of the net forward movement of detaching roller. Now, let us do take one practical example. Okay. Things will be simple. So, one practical example from the industry, let us see. A cotton comber is running at 240 nips per minute, has following details in the epicyclic gear. This is the same epicyclic gear we are using. So, forward movement 36 rpm, okay, in counterclockwise direction, that is positive, and gear train ratio is between the gear D and bottom detaching roller is -4, diameter of detaching roller is 25, as we have already assumed that gear A rotates at plus 116 rpm, okay, in counterclockwise direction, that is 1/4 of the combing cycle, and then gear A rotates minus 146 rpm in clockwise direction, that is a negative, during the fast forward motion for 1/4 of the cycle. Rest of the combing cycle, that is half of the combing cycle, it remains stationary. So, there is no movement of gear A. Calculate the net forward movement of the wave per combing cycle. It is basically this practical example is exactly same as the earlier one, only difference is that we have the gear ratio has changed between the output gear D and the bottom detaching roller. The counterclockwise rotation is positive of the detaching roller corresponding to the forward movement of the detaching roller. We can see these are the different from the gearing diagram we are getting this one, and here in the fast forward motion, in the backward motion first we will see, then fast forward and the normal forward. So, normal forward, in that case the A will have 0 motion. So, RPM of gear A is x plus y, RPM of gear B and C is y minus 1.5 x, that is this is 1.57, gear D is 1.82, this is x plus y, and RPM of gear F is y. Now, case 1, from the index diagram 6 to 16, again it is the 1/4 of the combing cycle, that means 1/16th of a second, assuming again 240 nips per minute. If we change the nips per minute, like if we make it higher speed, then the time duration will be less, that is only the difference will be there. So, backward movement of the detaching roller, RPM of the arm F is 36, RPM of gear A is given 116 counterclockwise direction, about 40th we have calculated. So, putting the boundary condition 1/4 of the cycle, 1/16th of second it will go. So, RPM of gear A is 116 x plus y, gear F is y, equal to 36. Therefore, gear X becomes, that is speed x becomes 80. So, x plus y 116. So, RPM of gear D we can calculate, it is 182 plus 182, and we can get the backward motion of the detaching roller will be minus 728, and it is going up for 1/16th of second. From there we can calculate the net backward motion. Net backward movement will be minus 59.35 millimeter. So, this is coming from 1/16 second. Similarly, in case 2, 16 to 26 index number 1/4 of the cycle, 1/16th of the second with fast forward motion, and RPM of the arm F is 36, and RPM of gear A in the clockwise direction, it is actually minus 146 from the rocking shaft. And if you use the boundary condition 16 to 26 index number 1/16th second time, RPM of gear A x plus y equal to minus 146. So, y is fixed, that is arm 36, x will be minus 182. Okay. And from there we can calculate the RPM of gear D, which is output of the epicyclic gear minus 295 RPM, and from there we can calculate the RPM of the gear that is epicyclic is detaching roller. RPM of detaching roller becomes 1180, which is fast forward motion. That much RPM it is moving, and this will move for 1/16th of second, that is fast forward motion of wave S2 we get, which is 96.61 millimeter, okay, that we are getting. And then normal forward, where A will stop its motion, very slow motion at a normal advance, the F gear will rotate in the same direction at 36 RPM, gear A is stationary 0 RPM. So, x plus y will be 0, and putting the boundary condition from 26 to 40, again from 0 to 6, x plus y will be 0 and y is 36. So, x will be minus 36, and using this two value x and y value we can calculate the speed of D. So, speed of D becomes minus 29.5 RPM, and it is for 1/8th of the second. So, 1/8th of the second. So, that D and RPM of detaching roller is 118 in forward direction, that is a normal forward for 1/8th of seconds. So, we can calculate the total forward motion, normal forward motion is 19 point, that normal forward movement is 19.32 millimeter, and we can calculate the net forward movement of the wave per combing cycle, S1 plus S2 plus S3, here minus 59.35 is the negative backward motion, fast forward motion is 96.61, and then 19.32 is the normal forward motion. So, effective forward motion is 56.58 millimeter. So, we have come to the end of the combing section, and in the next section we will start the next process, which is roving process. Till then, thank you.